This is a video about the electrostatic force. You might also hear this thing called a Coulomb force. So it works like this. Back when we did gravitation, we had an object here, like maybe a star, and then we had another object that was nearby it, maybe a planet or a satellite or something, and we said this thing had a mass of m, this thing had a mass of m, these had a separation distance of r, and the one exerts a gravitational force on the other and the other on the one. That was g m over r squared. The only thing that we need, the only qualifier we needed for this to be true, was for there to be two objects that had mass. Anything with mass attracted each other. And then from there we were able to get things like potential energy was negative g m over r. We were able to get acceleration, and we could do all these different pieces. Electrostatics deals with the attraction or repulsion, so it deals with the forces between charged objects. We were doing the forces between objects with mass, now we're doing the forces between objects with charge. So what it'll look like is this. We have an object here that has a charge q. We have another object here that has a charge q. These are separated by a distance r, and they exert forces on each other. This is an electrostatic force, so I do F sub E, and I get K Q Q over R squared. It looks a lot like the gravitational force. It's actually mathematically identical in form, which means however this gravitational force acts, that's really how this charged force will act. So there are some differences, and those are going to come in. With masses, anytime we had two masses, they had the same sign, right? We didn't talk about negative masses. That wouldn't make a whole lot of sense. But charges, we're not limited to that. So with charges, we can have negative charges. If we have two charges, so if Q and Q have the same sign, meaning both positive charges or both negative, then they repel. If Q and Q have opposite signs, they attract. So a positive and a negative. The force is most definitely going to be along the line that separates them. So if I've got an object here and I've got an object here, this one will feel a force in this direction or in this direction, depending on the sign of the charges, but it's not going to feel a force over here. That doesn't make sense. It has to be on the line that connects the two. Okay, a little bit more. This constant K, for gravitation we had that constant G. For electrostatics we have this constant K. K we call the Coulomb constant, and it is made of a fundamental constant, epsilon naught. It has a value of 8.99 times 10 to the 9th Newton meter squared per Coulomb squared, which we usually just say is 9 times 10 to the 9th. And we can look at this epsilon naught. This is 8.85 times 10 to the negative 12th, and that's going to be Coulomb squared per Newton meter squared. This thing is called the permittivity of free space. And there is a little bit of a hint in here already. This is dealing with free space. If I am looking at two charges that are separated by some distance and they are living in a vacuum, so no medium at all, then this is the permittivity that makes sense. If I'm looking in air, it's going to be ever so slightly different. Not enough to where we're going to actually treat it differently, but if I were doing this problem in water or in some kind of a semiconductor or some other material, then instead of using epsilon naught, I can use epsilon without a subscript, and that can be the permittivity of a given medium. This almost never comes up in this course or at this level. This is important for electrical engineering. It can be important for computer engineering, and it comes up once in a while in more specialized areas if you are doing maybe research on the electrical propagation in different body tissue. Then you'll be looking at a different value from that regular K Coulomb constant. You're going to be looking, I even threw the subscript on here, that's how often we use it. You're going to be looking at the permittivity of some other medium. So it does come up from time to time beyond this course, just not usually in this course. But it's a good thing to be aware of that it exists. So that's a force, Q over R squared. Now you know how to deal with forces already. We know forces can go into free body diagrams. We know we can say a sum of forces is a mass times an acceleration. Those are still true statements. We just now have a new force. We can add forces, but they are vectors. So if I've got this object here, and I've got an object over here, and maybe it's nailed down in place, and then I've got an object over here, and it's nailed down in place, we'll say Q1, Q2, and maybe we'll have this one be positive, this one be negative, this one be positive. Then I could say my force, I'm gonna move the label. I could say my force from Q1 is going to be an attractive force. So there's my F1. My force from Q2 is going to be a repulsive force. So there's my F2. And now I've got these two forces that I can add as vectors. I'm going to have to break one of them into components. I'm probably going to break F1 into components based on angles. So I'm going to have like an F1x an F1y, then I can add the x's and I can do the y thing and Pythagorean theorem and find my net force acting on this thing. That's how I'm going to do this. So electrostatic force still has units of newtons, still behaves exactly like any other force that you've seen before. It behaves mathematically exactly like that gravitational force. So if you zoom out far enough and you're looking at solar systems, or you zoom in far enough and you're looking at atoms, you get forces that behave the same way, which is all kinds of interesting on its own. The one thing to note that is going to be different than some of the forces that we've worked with, I mean, it's not different than the gravitational force, but it's been a minute since we've talked about forces. So the one other thing to note is that this force changes when we start moving things closer to each other or farther apart. So we've got a force that's not constant when we did like an F equals mg. For gravity near the surface of the Earth, that force was constant. Or when we did, frictional forces, like a kinetic friction, we did mu k times n. That was a constant force, and for those we were able to say the acceleration is constant. And then use our kinematic equations, right? We could say like an x final is x initial v initial t half a t squared. We were not able to do that when we had our big gravitation equation, or when we had our Hooke's law equation. With those, we were not able to use these constant acceleration equations, right? A equals changing. That's going to be true of this Coulomb force too. That's going to fall into this category over here. So, just a heads up, we can't use our regular kinematic equations with this